Okay, so here we go. Now let's look at the equation of motion again and have mq double bar double dot t plus c dam times q double bar, which is the one that works, dot plus k q double bar, this is our functions of time here, equals to f double bar t, right? Now, if we are now talking, I'm sorry, I shouldn't use f double bar t, I should have said we've already gotten to a name for this, and we are saying that we have a right-hand side under our convention that is L of t and 0, right? So at the measured coordinates we've got some loading, at the unmeasured coordinates we have no loading, right? And these loads are required to produce the same response whether this is k or this is k plus delta k, right? And this is that response that we're interested in. Now we're going to take a Laplace transform and get ms squared plus c dam s plus k, and that's going to be common factor of q double dot s now, right? And then this becomes ls and 0. Okay? Now if we multiply times the inverse of this matrix on both sides, then we have q double bar in s is equal to m s squared plus c dam s plus k to the minus 1 times ls and 0. Now this matrix here is the transfer matrix for the complete thing, right? So let's call it, I've been calling it Tm, but let's just call it G for shorter, right? So if we do that, then we can write this thing like this. I'm going to put that on the right side. I'm going to say the transfer matrix G, given our order, that would be G, Q, Q, right? And then we have G, Q unmeasured, G unmeasured, measured, and G unmeasured, unmeasured, multiply times LS, which is at the measureds, and 0, which was on that side, equal to these guys, right? Which are Q double bar on the Q, S, and Q at the U's, double bar, S, right? So that's what we've got. Now, we take and we say, all right, if that is true, and so far all we've said is if, then from this equation we find that G, Q, Q, right, function of S, times L, that's a function of S, plus this times 0 is equal to Q, Q double bar S, right? And how do I do this? Okay, and this is in the reference state, right? That's in the reference state. Now, I can say that in the damaged state, because everything applies equally to both, these loads are the same, the response is the same, I can say G, Q, Q, and let me use an ultra bar to say damage. So in the damaged state, this equation holds, right? And this is exactly the same because we've already argued that the response is identical when we have the loads L sub S. Okay? Now, if that is so, then we can subtract these two equations and we can say that the change in G, Q, Q multiply times LS must be 0. And so we've arrived, after all these derivations, at the desired result. which is that the Laplace transform of the loads that we are trying to find, those loads that would produce the same response in the references and in the damaged state, and that are restricted to be defined exclusively at the measured coordinates, the Laplace transform of those things that we're looking for are simply vectors in the null space of the change in the transfer matrix at the measured coordinates. Now, the transfer matrix at the measured coordinates, we know how to calculate from the data, right? In fact, last class, we just showed how that is done. Particularized it to flexibility using s equal to 0, but using s is equal to whatever, that's what the transfer matrix is at the measured coordinates. So we know how to get GQQS and G bar QQS from system ID, right? So we can get this from ID, and we can get this from ID, right? So without knowing anything about the structure whatsoever, just simply from data, we can get these two matrices. We can subtract them and get this one, and by algebraic manipulations, right, which is a singular value decomposition, we can find what is the null space and therefore what is these vectors. So we can extract the vectors L as a for any S that we require, right, from the null space of something that we can compute from the data without knowing anything about where the damage is and without knowing anything about what the structure looks like. Okay? So now that we have those vectors, let's see, once we have those vectors, then what we are saying is, well, okay, so those are the vectors in the Laplace domain. What I really want is to find what is the effect of those loads, right? Because what I am going to detect my damage is by looking at where in the structure is there no stress, because the regions where there is damage are stress-free, because that's the only way that the response is identical in the two states. So to do that, there is a way to try to go back to the time domain, and it's explained in the original paper and so on, but it is much more practical to operate all the time in the Laplace domain. And I think I can show you without too much trouble why that is so. So imagine that you have, again, M, Q, let's say double dot, right, T plus C damping times Q double dot, oh this was two dots, this is one dot, T plus K times Q double dot. Of course we don't know the damage, so we can, but now I'm talking about the K of the system in the reference state, right? And then this would be LT and 0. So these are our famous loads, right? For which we know their Laplace transform. How? By taking the difference of the transfer matrices from data and computing the null space. So then we say, okay, let's take a Laplace transform here. So this is ms squared plus c dam s plus k, right? And then that is times q double bar s, and that's equal to ls and 0, right? So that looks like that. Now, what is this? This is some sort of a matrix that we cannot compute unless we have a model, right? So at this point, well actually no, I'm going to say that, but let me go one step further. Inverting this matrix, I get that Q double bar S is equal to ms squared plus c dam times s plus k to the minus 1 times ls and 0, right? Okay, so this is what? This Q double bar S. That would be the displacement field everywhere in the structure, right? Due to, in the Laplace domain, due to the loading that produces zero stress everywhere. So for short in notation, let's say that we take this Q sub S and we call this here G of the model. So at this point we were able to get L sub S with no model, but to go further and calculate the stress field everywhere, we do need a model, and the price that we pay here is that we need the mass, the damping, and the stiffness of the model. In the previous case, in the DLV approach, we were operating at S equal to 0, right? And for S equal to 0, you can see that these two terms disappear, and all we would have would be K. I'll come back to that in a minute, but let me just say that we call this G of the model. Now, G of the model multiplied times Fs, and what I'm calling Fs is equal to the vector Ls and zeros, which in practice I don't need to have them segregated. This vector simply means this is equal to Ls at the measured coordinates and is equal to 0 at unmeasured coordinates. So this can be in any order you want, right? Now this is now the displacement field in the Laplace domain at the selected value of S. G of the model is a function of S, of course. For the purposes of practical computations, we tend to think, engineers, structural engineers, we tend to think more directly in terms of finding stresses due to loads, not finding stresses due to deformation fields. Because what I could say right now is that all we need is to look for the deformation, for the stress field associated with the deformation pattern Q sub S. But we can convert this to loads conveniently by simply multiplying this deformation field times the stiffness matrix in the undamaged case. So we get K times G of the model times F sub S, and we can say that the loads LST, which are a function of S, when applied to the structure will produce the desired zero stresses in the regions that we are looking for. So the final what should I say? The final form of the DDLV method is this approach. I mean, it's this expression. So the DDLV method states the following. You need, or not states, but is as follows. You need to have the stiffness matrix of the system in the undamaged state. You need to have the model transfer matrix at the selected value of S, which is this. Obviously duplicates the stiffness, adds ms squared and c dam s. And you need to have the vector Fs, which has zeros everywhere except at the location of the measured coordinates, is equal to Ls. And what is Ls? Ls is the null space of delta G QQ, right? Evaluated at S. Null space of delta G QQ evaluated at S. Now, that's it. If we considered, now I know that at this point this can be quite, perhaps, I don't know, could be confusing, it's a lot of new information. But let me just indulge for a second and see what happens if you were to apply, do I need to do this here? Look what happens at S equal to 0. Because S equal to 0 is just a particular location, right? So if you took S equal to 0, you will get that LST is equal to K, right? But now what is G model? Well, G model now, if S is equal to 0, is just the inverse of K, right? And so you get Fs here. So this is just the identity. And then you find that LST is just Fs, right? And what is Fs? Fs is equal to Ls, right? That's 0 and zeros. So, and what is Ls? Ls was the null space of the change in the transfer matrix. But the change in the transfer matrix at S equal to 0 is just the change in the flexibility, right? So what we see here is that this situation is just the DLV approach that was presented previously, okay? Where Ls is just the change, LL0 is just the change, is the null space of the change in the flexibility. In this case, we can select S arbitrarily and compute many more loads to calculate the stress field to locate damage. Yeah, one thing. These vectors, LST, are complex in general. And at first glance, sometimes people get a little bit surprised. What do you mean a complex load? Well, there's nothing to it. I mean, if the load is complex, the load is complex. So for example, you may find if the damage was here, and you had sensors in this, I don't know, let's say here, to make it easier for me. So let's say the damage was here, you may find that the LST, and you had sensors, let's say, in these two levels. You may find that this vector is A plus BI, right? And that the vector over here is just simply A plus BI in the other direction, right? So when you find the stress field, you find that the stress field, they don't combine the reals and the imaginary, right? So you have, if you can draw it complex if you want, so you could say that the complex stress field is shear, in this case, A plus BI, and then zeros, right? It could be that this could be like this also in this particular case, C plus DI. And so it might go like this. And so we find that we have the damage only here, right? So the stress field, and this could be moments or shears or anything, when it gets applied in the more general structures other than the shear building, that they could be, that these stress fields are complex. So when the damage is located, the stress field is 0. That means that the real part and the imaginary part is complex, is 0. So sometimes, and perhaps most times, I tend to work with the absolute values. That is, once you plot the stress fields, you can just say, okay, absolute values of this thing, so you just look at real numbers at the end. Okay? Now, you cannot take absolute values beforehand. Or you should not, because these additions take place in the complex field, right? And then you take the absolute values. All right, so let me see. This is essentially the application of the approach. So what I want to do now to conclude, well, there's quite a few little details that remain, and I will try to remember them as, and to give you at least a comment, as I explain or lay out the sequence of what you would do to do the last homework problem, okay? So the last homework problem is intended, homework problem number 12, which I've already solved using actually data. I simplified it for you by giving you the matrices, but first let me say DDLV in general as a summary, right? So you have data, and this data is input-output in the case of the DDLV. There is a stochastic version which is for when you only have output, but in this case we're talking about the one where you have both input and output. So from input-output data, you perform an identification, and from the identification you get let's say A0 in discrete time, B0 in discrete time, Z0 in discrete time, right? So once you have that data in discrete time, you do a discrete to continuous transfer, and now you have A0, B0, and Z0, okay? Then you have data again, input, output. This is the reference state, and let's say this is where you think there is damage or has been already determined that there is damage, and we could call it A1D, B1D, and C1D, right? You perform a D to C, and now you have A1, B1, and C1. So what I have given you in the homework is already this. So I have bypassed, for your convenience, instead of giving you input-output data and asking you to perform an identification, I just gave you the matrices of the identification already. But the matrices that I'm giving you, A8 and so on, are actually not from the system but from identification, meaning I took data and I did the ID and I gave you the matrices, okay? I took data, I did the ID, and I gave you the matrices. In order to do this, not only did I have to do the ID, but in reality you also, normally if there is only one input, right? This process also involves expansion so that you have this B matrix. Oh, wait a second. No, I take that back. I take that back. I have not done the expansion. Ooh, I was about to really mess up there. The matrix that I am giving you here, this B has only one input. And now I just remembered that I probably missed providing the information in the homework statement, so I will go change it. But it is necessary for you to know, in order to be able to do the expansion for the transfer matrix, that the input is at the second sensor. There are 4 sensors, okay, in the homework. There are 4 sensors, sensor, 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 and the input is collocated with the second sensor. That's necessary to be able to calculate the alphas that are needed to do the transfer matrix. Okay? Maybe I put it and maybe I'm not remembering, but in any case, that information is necessary. Okay? So, you have your A, B, C from identification. You do discrete to continuous, you get these things. Then, from A0, B0, and Z0, and you select some S value in the Laplace domain, you get a G0. That's going to be only at the measured coordinates. With A1, B1, and C1, which are already in continuous time, in the damaged state, and the same S, you get G1, right? Now that you have G0 and G1, then you get delta G, which is just G1 minus G0, right? So that's the change in the transfer matrix. Once you have the change in the transfer matrix, if everything is correct, then that delta G is rank deficient, assuming that the damage is not more than the number of sensors, the rank of delta K. And then this delta G has a singular value decomposition, right? Has a singular value decomposition. And in the ideal world that we're looking at right now, some of the singular values will be 0. In the real world, where there is noise and so on, there will be never singular values that are exactly 0, but there might be some that are very small, and you can tell that there is some sort of a quasi-null space. The point is, anyway, that these vectors here that we see on this side are the vectors LS, right? Now there may be more than one, because there might be two zero singular values, or two or three or whatever. In the discussion that I've given you here, I've assumed that you select one of them. Needless to say, it is possible to calculate results for all of them separately if you want, and combine results. But say you take LS as the vector for the last singular value only. So that's the selection I'm making here. So you take the last vector here, and that's your LS. Then now you take, you calculate G of the model at the selected S value as ms squared plus C damping times S plus K to the minus 1, right? So that's your G model. Then you compute LST as the stiffness matrix K times your G model times your vector Fs, where your vector Fs is, as I said, the same as your vector LS, but it's blown up with zeros at the unmeasured coordinates. Now that you have your vector LST, which is a complex vector, then that vector LST gets applied to the structure. So now you go to your model, right? In this case I'm using a building, could be anything. Notice that the vector LST is not restricted to the measured coordinates. The non-zero values of Fs are restricted to measured coordinates. But LST is non-zero everywhere. So you get something like this, right? And each one of these things is complex. And so on. If you were doing a generic structure like using frame 2D, that would be fine. You can apply the real part of the loads if you like on one set and get the real part of the stresses. Then you can apply the imaginary part of the loads on the second analysis, get the imaginary part of the stresses. No big deal, right? So you can do that, you apply your LST. In the case of a shear building, then that will give you some sort of a shear plot. That is not a good idea what I'm drawing here, because you might be saying, what is the size of that? So let me just do it this way to be more precise, and I apologize for my error last time. This could be something like this. Where this is the real part of the shears. And you can do the same thing for the imaginaries, right? Whatever. So the zeros will coincide on both cases, right? Imaginary part of the stress field, which will locate your damage equally. So that's pretty much the basics of the DDLV approach. There are, of course, many subtleties that arise, not many, but there are some subtleties that arise, and I will just mention one of them that is perhaps the most relevant. When you do the ID, don't necessarily get the order of the system, right? You get the order of whatever was identifiable. So if we had a building with 20 floors and so on, you know, maybe you get 5 modes or something like this. So it's important to remember that you don't necessarily find all the modes. So whenever we're saying A and B, we shouldn't think that those A and B matrices correspond to the actual model of the system. They correspond to some sort of a truncated version, right? Modally truncated version. So if you look in terms of the complex plane, and you have here the real of S and here the imaginary of S, right? Remember that the eigenvalues of a system have a real part and an imaginary part in I, and that they usually come, well, in complex conjugates for systems that are underdamped, right? The real part being small because it tends to be omega psi or omega c, and the other part is the damped frequency. So let's say, for example, that your system was such that you had these 3, let's say that you identified 3 pairs of complex eigenvalues, and that if you plot them on the complex plane, they would plot like that, okay? That would be imaginary of lambda. So let's say these are poles. So you can plot the poles in the S-plane. Right? You can plot the poles in the S-plane. So let's say these are the poles that you were able to identify. Now you can make the reasonable assumption, which will be satisfied always pretty much, that there were some poles that you could not identify. And you don't know where they are. They might be here. There might be another one over there. Hopefully, and this need not be exactly true all the time, but hopefully the poles that we could not identify are after the ones that we identified when we look at it in the imaginary. There's not somebody hidden here in the middle between these two, for example. It could be, but we're assuming here that, let's say that the poles that could not be identified were outside the band. Now, when we select S values to do the DDLV approach, we should not select values of S which are closer to unspecified poles, unidentified poles, than to the identified poles, because in that case the influence, remember that the transfer matrix, using the notation from last class and from the homework that you're doing, right, was something like this: phi whatever comma I, right, multiply times phi whatever comma I transpose times alpha I divided by S minus lambda I to the P, right? So you can see that when you calculate the transfer matrix at a given S, the term that has the most effect is the one that is closest to that pole, right? So if I take an S value here, then at that S, this pole and this pole have the most effect, and then this one least, and so on, right? However, if I take an S over here, then that S will be dominated in reality due to the, not that S, the transfer matrix in reality should have significant influence from this, but we can't get it because we didn't know what these are, so we would be calculating it using only the black dots. Therefore, at this S, our results would be very poor. Right? So we don't want to select S values which are outside the range of the identified space of the poles. So if you say that the pole with the largest imaginary that you had was the third dot there, right? So this is the region where we identified our poles, right? And because this comes in complex conjugates, we use the results over here are just conjugates of this. So that means that we should specify S values that in some sense are restricted to this region. Now you could ask the question, what about this point here? No, wait. Using the same coloring scheme, I should say, what about an S value that is over here? Is that all right? Well, you know, that may be all right. It's just going to depend on the distance to the poles, right? So these are the distance to the poles that we actually have. And then there are the distances to the poles that we don't have. And we don't know where they are, but they exist, right? So there is a distance of this to this. There is the distance of this to this, and to this, and to this, right? So we would like to overwhelm the effect of the transfer matrix by the stuff that we computed to minimize the effect of the stuff that we're not able to identify. For that reason, it is a reasonable approach to stick to S values that are in the region so that no S has, let's say, an imaginary part that is larger than the largest identified pole. Now, you could actually do a research project. People have written theses on this thing and so on. It still remains kind of a little bit of an open question. How about, is there such a thing as an optimal S selection? You know, I have often provided recommendation that S values be selected. Let's say you take identified pole and you make some sort of a circle, you know, and you say, well, okay, I'll try to stay within circles that are around the poles that I identified, and the circles have some diameter. That's one possibility. Another possibility is just to say, don't worry too much about it. You don't have to be that precise. And it's usually a good idea to select S values on the imaginary. So you can just select S values, let's say, here, right? Here. They tend to be closer to these guys because these guys are very close to the imaginary. In fact, in the homework problem, I think I said try using 10i. As a recommended value, but you can use 10i, 11i, 12i, 15i, minus 2 plus 7i, and so on. You can try different values. I think in the homework problem it will not be an issue because the matrices that we have in the particular case of the homework, I think, I'm almost 99% sure, are complete, meaning that if we have all of the poles, that is, if the poles, let's say the system really was 3 degrees of freedom, so it's order 6. Then there are just 3 poles and the 3 conjugates. In that case, there's nothing in red, so even if you take an S value that is over here, all right, the answer would still be correct because there is no unidentified space that it's affecting the result of the transfer matrix at that S. It may be that the resolution is not so great, for reasons that you can only learn by trying it yourself, but there would not be a wrong answer. However, if there was unidentified space with red stuff over here, then they may be the ones overwhelming this point. Okay? Okay, so I think also in the application of the DLV, or the DDLV, whether you select one S or 2 S's or 10 S's or 100 S's, it's up to the user, right? If everything is well, then the results in all cases will point to the correct location of the damage. When there is, as is always the case in real life, error, because there's noise and there's all kinds of other things, then with some cleverness, one can help the cause of getting the right answer by looking at how the answer looks at many different values of S, right? You would expect that as you aggregate results from many S values, that you will tend to see the correct picture, even if there is noise and approximation in the data. Okay, so as I said, the homework 12 has been posted. That is the last homework of the class. This is the last lecture. We do not have any final exam, so I will wish you the best. Hope you enjoyed and learned something in the class, and you have till the, when is it? The end of next week, I think it is. Something like that, like Friday, right? Friday the 24th, I think it is, for completing anything that you left undone. And then I will take a look at the whole submissions and you know, assign everyone a grade. All right.